In this lesson, we're going to take a look at elements and the periodic table. We are going to move through material relatively quickly, as it should be primarily review from last year in grade 9. So when we look at the periodic table, we want to recognize it as a structured arrangement of elements that actually helps us to explain their physical and chemical properties. It's not random positioning of the elements. They're all there specifically due to either a physical or a chemical property. So as we look at the periodic table, we can notice everything, or the majority of the elements to the left, have a silver color and are primarily solids. When we look to the right-hand side, we start seeing different colors, we start seeing different states, and that's all due to the arrangement of the subatomic particles in the atoms. So a quick reminder when we talk about properties and changes, property is like an adjective. So when we're talking about a physical property, it's describing what the substance is like. So if we look at this match, it's saying it has a red tip, it's made out of wood, it is long and narrow, it is solid. Whereas when we're talking about a change, that is a verb. It's describing something that the substance or the element is doing. In this case, if we're looking at the match, we could say it is burning, it is on fire, it has changed color. So it's an active word. Okay. There are characteristic physical properties of all the elements in the periodic table, and that means it's a property that is unique to that substance, and therefore it can be used to identify that element from the other elements. So one of the key ones is density, which you would have learned in grade 9, which is mass divided by volume. So it's basically how much of that substance is in a particular space. They're freezing points, so the point at which they become a solid. They're melting points, the point at which they go from a solid to a liquid. Boiling, going from a liquid to a gas. Now, those are all important in terms of everyday uses. When you have a light bulb, we want to know what the melting point is of the material used across, because we don't want our light bulb to melt every time we turn it on. Whereas there are fuses that use metals that when there is too much electricity, it does heat it up and it will cause it to melt and break, thus keeping the circuit safe. Okay, so characteristic physical properties are used as identifiers for each individual element. In the organization of the periodic table, there are particular groups. Now, these are columns of elements that have things in common with each other. So they are vertically arranged. They're also known as chemical families. And elements within a family or within a group have similar chemical properties or similar ways that they will react. So elements, the reason that they have these similar chemical properties is because they have the same number of valence or outermost electrons. So if we look at the alkali metal family, they all have one outer electron. Alkali earth all have two. We're going to skip the transition metals because they break the rules a little bit. We'll hop to the other side of the table. Boron family all has 3 outer electrons. Carbon, 4. Nitrogen, 5. Oxygen, 6. Halogen, 7. And noble gases, 8. Or a full outer shell. So how many valence electrons they have determines how that element will react. So their group number that are found on the periodic table actually tells you the number of valence or outermost electrons. So group number 1 has 1 valence electron. We call those the alkali metals. So if we look at lithium, sodium, and potassium, they're all silver, solids, shiny metals. They all form compounds that are mostly white solids. So compounds meaning when they combine with something else. And they're all very soluble in water, meaning that they will dissolve or dissociate or break apart when put into water. Group 2, meaning 2 valence electrons, are the alkaline earth metals. They are also shiny, solid, silvery metals, but they are not quite as soft as the group 1 metals. They form compounds, however, that are insoluble in water. So when they bind with other elements, they are generally insoluble or don't dissolve or break apart when in water. Examples are magnesium and calcium. Group 7, or sometimes referred to as 17, so we're hopping to the far side, are our halogens or our halide family. They are all non-metals. They're all poisonous in their forms, and they react readily with sodium and other alkali metals to form salts. So oftentimes we think of sodium chloride as salt. That's a common salt, but anytime we have a halide with an alkali metal, we have a salt. So we have fluorine, chlorine, bromine, and noticing they are in different states. Some are gases, some are liquids, and iodine is a solid. Group 8 or 18 are noble gases. They're very unreactive because their outermost shell is full. They do not form compounds because they are not reactive. Examples are helium, neon, argon, krypton, and xenon. Now, periods are the rows across the periodic table. So horizontally looking across, anything in the same row is in the same period. They also use a number system going from 1, 2, 3, all the way down to 7 in the bottom row. And each period represents the electron shells or number of orbits. So if they're in period number 1, there's 1 electron shell. Period 2 has 2 shells, and so forth as you go down the table. Now, there are some other divisions in the periodic table, mainly metals, nonmetals, and metalloids. So metals, they're all shiny, malleable, ductile, conductors of both heat and electricity. Most of them react with acids to produce a gas. Most are solids at room temperature, that is all except for mercury, and they are found to the left of the step ladder on the periodic table. Nonmetals, however, are all dull, brittle insulators, meaning that they don't conduct heat or electricity. They do not react with acids. They can be found as solids, liquids, and gases at room temperature, and they are found to the right of the ladder, except for hydrogen. It's off on the left-hand corner all by itself because it has 1 valence electron, and it fits better over there in terms of number of electrons. Metalloids are substances that sometimes react like a metal, sometimes act like a nonmetal, and they sit on that staircase. So elements with properties of both metals and nonmetals, and they sit on the ladder between the metals and nonmetals. So let's take a look specifically at atoms and the numbers. So looking at some common things, ways to identify all the elements in the periodic table. An atom, when we use that term, we're talking about anytime 3 things are equal. So in an atom, the number of protons and electrons are equal. That makes an atom neutral. And how do we figure out where to get them? We look at the atomic number. So if we look at this atom here, we notice that there are 3 negatively charged electrons. There are 3 positively charged protons. So 3 negatives and 3 positives gives us a net charge of 0. Neutrons in the middle are neutral, 0 charge. So this would be an atom because it is neutrally charged. Okay? We can identify it by looking at the number of protons. There are 3 protons, which means atomic number 3 is lithium. Okay, the atomic number is like the thumbprint of an element. Okay, that tells you how many protons. You cannot change the number of protons, otherwise you have changed what that element is. Okay, if we look at sodium, it has the atomic number of 11. Therefore, an atom of sodium has 11 protons and 11 electrons. So how do we calculate the number of subatomic particles in the atom? Well, as we just said, we look at its atomic number. So for carbon, it's 6. That would tell us there are 6 protons. Okay? We can do that for any element in the periodic table. To figure out the number of electrons in an atom, it's the same as the number of protons because it has to be neutral. Okay? Now, how do we figure out how many neutrons? We take a look at the atomic mass and we subtract the atomic number. So for carbon, it would be 14 minus 6 gives us 8 neutrons. The reason is the only subatomic particles large enough to contribute to mass are protons and neutrons. So if we know how many protons there are, and we say if our total mass is 14, 16 pieces of that mass are accounted for in protons, means the leftover pieces have to be made up of neutrons, and each one has an atomic mass of 1. So with the atomic mass, the reason it's not a whole number is it is the average of all the masses of all the atom types of that element. So if we look at carbon, there are some atoms of carbon that have a mass of 12 and some that have 14. Now we can't change the number of protons because that's like its fingerprint, that's its identity, but the number of neutrons can change in the nucleus. Okay? So when we have 2 versions of an atom, we call those isotopes. So they're atoms with the same number of protons, but different number of neutrons, which means they have a different mass, so different forms of the same element. Okay? Hydrogen has the same. There is a hydrogen with an atomic mass of 1, 2, and 3. Okay? Differentiated by its atomic mass. number of protons remains the same. So sometimes you'll see elements referred to or written down in standard atomic notation. This is because it represents all of the subatomic particles relatively quickly. So you write the symbol, you write its atomic number or the number of protons, and then up top you write its atomic mass. And because you're given the mass, you can calculate the neutrons. So in this case, we have 3 versions of carbon, each one by the mass indicating how many neutrons are present. So what is the difference between an atom and an ion then? An atom is our basic unit of matter, and it is neutral when protons equal electrons. An ion, however, is an atom or molecule with a net electric charge, and that's because it has gained or lost electrons. If it loses electrons, it has a positive charge. If it's gained electrons, it has a negative charge. And the reason it gains or loses electrons is to have a full outer shell, based on the octet rule, which gives it stability. So we have a sodium atom. Notice it has 1 electron in its outer shell. It will lose that 1 electron. It donates it to another atom elsewhere. And it now has a full outer shell. But because it lost 1 electron, it has an overall +1 charge. So ions can be positive or negative. If they're positive, they're referred to as cations. I think of it as the T in the cation kind of looks like a positive charge. So those are any ions that have lost electrons. Anions are negatively charged, and I think the line across the A kind of looks like a negative sign. Those are ions that have gained electrons, those on the right-hand side of the periodic table. And to name an ion, we drop the ending of its name and add IDE, okay? So if we want to take a look, hydrogen becomes hydride, fluorine, fluoride, chlorine, chloride, nitrogen, nitride. Okay, so based on the fact that they are charged, we give the ending IDE. I will leave you with this cartoon. Now that you fully understand ions, you will find it hilarious.